Like,
You're gonna be so popular.
I will finally be searchable.
You've got like 9 subscribers.
yeah, but
Make that YouTube money. That was good.
Alright. So,
I don't want my. I'm gonna like try my hardest not to be in the video.
you can just slide your whole desk back if you don't want to.
Mallory,
you
you're in
shouldn't.
this one.
I mean, you shouldn't be, but are they
Still in
good?
it, Mallory. I don't want to block it.
Now are they good?
Yep.
Okay.
Yep.
I'm just saying.
All right. But if you lean forward to talk to Pasta, you'll be in.
Okay.
Okay.
Oh my God.
All right. So I emailed your parents yesterday. I told them about the new YouTube policy that will be added to my syllabus for next year. But since you're halfway through, that was the syllabus change. Okay, that was the official rollout of the new YouTube I Missed Class policy. Okay, so keep that in mind. If I have to do more work to film and to upload it, I mean, it takes a long time to upload a YouTube video. You think in today's world it would be a snap. But the videos are usually 20 to 40 minutes long. Not always, but because I film the whole class. Eventually, I want to get to the point where I have what's called a flipped classroom. Has anyone heard of a flipped classroom?
I think I
No.
Okay. We all turn upside down. Yes,
Okay,
we have
alright, let's
class
start.
during headstands. No, what will happen, hopefully next year, is that instead of coming to class and listening to me lecture, I will send you home with a note sheet and say, watch my 15-minute video tonight for homework. So that when you come to class the next day, we can practice everything we already learned. Okay, because you spent 15 minutes learning it on your own, filling out your note sheet, and then when you get here, we can do it all together. It works really good in math classes, because think about how a math class is run. She takes the whole class to teach you,
Yes, she does.
and then she sends you home,
Yeah.
and you have no help, right?
That's really true. Actually.
Imagine if you flipped your math classroom, and she did the lecture at home and worked out 2 or 3 problems, and said, okay, this is your homework. Come to class prepared to do your homework. So then you all walk in the next day, and everyone gets out their book, and everyone starts working, and she's there, the owner, the expert, owner of the information, and you do your homework in class.
Can we
Oh,
actually?
that would be-
Yeah, I feel like that
Wouldn't
would
that be
make me
great?
learn so much better.
Okay, so we're going to do that same thing, but we're going to do it with biology. Okay? And this is a brand new concept that's coming out in education. And I realize, and some people are taking it a little too far and saying, well, why do we even need teachers? Let's just have schools that are based off of Khan Academy. Have you heard of Khan Academy?
Yeah.
You put your hand down, I'll get your question. And lots of people say, why don't we just have Khan Academy schools and every kid gets a computer and comes in and sits down every day and learns from Khan Academy, and videos are so useful. Well, it's the personalized relationship between a teacher and a student that helps it to become real for you. So if I were to sit you in front of a computer every day and you hear my voice, can you ask questions?
No.
Not as easily. Okay? Do we get these funny little mnemonic devices and these stories and these real life episodes that help you say, I totally understand this now. I get it. I see where this happens in life. Because how many times do y'all ask that question? When am I ever going to need this?
A lot.
Right? Okay. So, yeah, triangles. Why do you need triangles? Well,
Yield signs.
I'm about to move into a house. Okay? I have to paint the walls. I signed on my house today. I'm pretty excited. I have to paint the walls. Okay, so this is one example, perfect example. I have to paint the walls. Math, you oftentimes think you don't need math. You use math every day. Okay, I'm about to use math today, big time. Okay, triangles. Is every wall perfectly rectangle?
No.
No. Some walls, especially in living rooms, have a rectangle and they go up like this and peak. Right? A gallon of paint will cover between 350 square feet to 400 square feet. I have to go through my house, specifically my living room, and measure, break it all down. So if this was a kind of like a house shape, a square at the bottom and a peak at the top, I'm going to have to figure out how far across it is and how far down for just the square, and get the surface area. What's the surface area of a square? Length times width. Okay, or if it's a square, perfect square, it will be side times side, because they be the same, or side squared. And then I have to try and figure out the surface area of a triangle. Do you remember the surface area of a triangle?
Half the length times
Half length times height, or base times height is what I think they call it for triangles. Okay, so I'm going to have to go through my whole living room, every single wall, deduct the space for the fireplace. So I'm going to add things in and take things out, and windows have to be removed, and I mean, I've got to figure out how many gallons of paint I need, right? What
Yeah, I would probably just get.
Well, if I go and I don't buy enough paint, when you buy multiple gallons of paint of what you think is the same color, you always add them together in a 5-gallon bucket. Because paint can be off by just a little bit, and then if you paint this wall with this gallon of paint, and then you run out of that gallon, and then you start this wall, you can have a tiny tint change. But because it's on an entire wall, it's really noticeable. So if I run out of paint, and I don't have enough, then I have to go get another gallon that wasn't mixed in, and it could have that change. So you always want to overshoot.
I have a problem solving for that.
Okay.
What you do is you go buy primer, and you put the primer on the walls.
Yeah, but that's a whole nother coat of paint I gotta do.
Yeah, but I think
Don't you have to put primer
You don't
anyway?
have to do primer.
But it makes it look better.
I don't like these. She just doesn't want me painting my room.
You can do it.
Mine is white,
If it's
okay?
brand new sheetrock,
Uh,
you have to use primer because it helps the paint stick. But if it's already been painted, that other paint will help it stick. Now, if it's glossy paint, like there's different sheens of paint. If it's glossy paint, then you probably do want primer because gloss is that shine, that shimmer, and that will help paint peel off if you don't give it something sticky to stick to. My dad was a painter, so I know a little bit. And she made us say we need primer because your walls are dirty and have stains, and if you don't prime something that has a stain, the stain will bleed through the next color, unless you painted like navy blue or something. Our living room is going to be like slate blue. I'm really excited about that. Okay, so math is important. Moral of the story, math is important. You use it every day, okay? I use it literally on a daily basis because when I go to the grocery store, I say, okay, this one is $3 and this one is $4, okay? Same thing. This one only has 12 ounces in it, while this one has 16 ounces in it. Which one's the better buy?
Isn't that what's in that little orange little square?
Sometimes it will put it on there for you. Like PetSmart puts it on there for you. Sam's puts it on there for you. But Walmart does, do they?
Yes.
On some stuff, but not on everything.
Walmart just lets you guess.
Yeah, so I bust out my calculator in the middle of Walmart, and I say, well, what's $3 divided by 12 ounces? How much am I paying per ounce? Is it really better to get the bigger box and pay a little bit more, or is it not? Because sometimes it's not. So I use math every day. Every day. I'm really a saver.
You really are.
Sure. All right, so I know you think that math is dumb and that you don't ever use it. Now, proofs, I've never had to prove to anyone that a triangle is this. Okay, that's just a good process for being able to justify your answers. Okay, so I can't give you that one. But lots of this geometry and this algebra, you use algebra all the time. Okay, shopping, every girl loves to shop, right? Okay, it's 40% off. How do you figure that out? Okay, the easy way to figure it out is you say, well, if it's 40% off, how much am I paid? If it's 40% off, what percentage are you paying? 60. Okay, so you take the 6 and you say it's $20, but it's 40% off. So 6 times 2 is what?
12.
It's $12.
Whoa.
Wait, what?
This is why they don't take in shopping.
How did that?
Well, if you do it by the 40%, you're only calculating what you're not paying. You're not calculating how much you're paying. You could, but that's a whole nother step.
See, I do like Yeah, let's just stick with it. Yeah.
So if you take the amount you are paying, which was 60, and multiply that by the whole price, you get the exact amount it's going to cost you when you walk up to the register. Instead of what you're not getting and then subtracting it from the total. How much would you multiply? 80. Does that make sense? Way faster. Yes. Let's go. Here we go. All right. So from yesterday, that's a reason flipped classrooms are important. You got to be able to do the work when the expert's in the room. But it doesn't always work, like I said, because teachers are awesome. And we don't want to learn just from computers. So I will eventually get to that point, but for now, when you're absent, watch the video. All right, protein synthesis. Let's review a little. Where do we get the directions for our proteins? From DNA. Very good. Is it the number of A's, T's, C's, and G's that's important? No. What is it? The order or the sequence they come in. Okay, and we see this as AGAT makes 0 sense to us, but after today, you're going to see this as words, and you're going to pick it up. It's going to make a lot of sense after today. All right. Now, why is protein synthesis important? What do proteins do?
They can make or break things.
They can build up things. They can break things down.
And then they can turn on other things.
They can turn on things, turn off
Turn
things. What else can they
Oh, Nicholas.
do? Close. They can build things. They are our structure. Okay. Not only do they cause reactions to happen, but they are our structure. They control everything in our body, how we're built and how it works. We have a lot of proteins throughout our body from top to bottom. What are the individual building blocks for DNA? Nucleotides, okay? So the sequence of nucleotides is important. But then what are the individual building blocks for proteins? Amino acids. Is the sequence of amino acids important? Yes. If we swap 2 amino acids, we have a big problem. And we're going to do an activity today to show you that. Okay, so these are our amino acids. Once we have a bunch of amino acids in a chain, we now have a protein. Very good, a protein. So amino acids can be by themselves. Okay, they're floating around in your cell getting ready to be put into a protein. But once you have 2 together, remember there's a book in the world that says when 2 are gathered together, okay, I'm in that place. Remember there's that book? All right. Same thing here. When 2 amino acids are gathered together, a protein is in the midst. Okay? All you gotta have is 2. Does that make more sense now? That book? Okay. All right. I'm on the internet, so I can't say the name of the book. All right. You may have heard of other books as well. All right. So amino acids, they have funny names. Do you all know what I'm talking about?
No.
All right. So amino acids.
She's trying to be polite.
We're trying to be PC in here, okay? I don't know what y'all do on Sundays or Saturdays for some of you. All right. So amino acids have funny names. I don't care if you butcher them completely. Just figure it out, okay? I will most likely pick up on which one you're trying to say. All right. So just sound it out. It's easy. And then we know that even one amino acid change can change the entire structure of an organism. And we're about to do an activity to show you how that matters. All right. Primary structure. What does that depend on? Primary structure of a protein. You're looking at it right here.
I'm trying to think of the word. It's like hydro.
It says it on the board.
The function.
It's simply the order. Simply the order. Okay? It says it right here. Right under the name. All right? So it's simply the order that they're in. Okay? And then once we go to the secondary structure, this is when we get the helix, or the folds and the bends and things like that. What does that depend on? How do we know which way it's going to fold? Now think of those words. Hydrophilic areas. Hydrophobic amino acids. What about an amino acid that has a negative charge? What is it going to want to be by? I can't hear you. Were you actually answering, or were you just thinking still? I thought your lips were moving, but I'm not really sure. Okay. If there's a negative in the environment, what are negatives like? Positives. Okay. Opposites attract, right? So if there's a negative amino acid right next to another negative amino acid, are they going to want to bond into each other?
No.
No. They're going to try and be further apart. All right. And if they're further apart, they're even going to try and find a positive to hook to. All right. So let's do our activity.
Yeah.
Hands live, please. I'm going to start frisbee and stuff.
Can I have like a red or a pink?
It's 1 protein per table.
What about that?
We can go here. I catch people.
I don't know if it's going to work.
We'll share with you. Yeah, we're supposed to share with you. We'll figure it out. Don't worry anymore.
All right. Watch your eyes, folks.
Made it.
Oh, you got that little bounce when you
I heard you can take a 37.
Oh, it's styrofoam.
His aren't set up. Okay.
I messed it up.
Yo,
I messed it up. I
please
messed it up.
Unfortunately, one group is not going to participate because Mr. Elliott's are not set up.
Alright, let me play.
Here's what I'm going to do. Brayden, will you hop across the way? And Paulina, will you join that? Just, okay. There, problem solved. Yes, it is true. All right, keep in mind that what I'm giving you is plastic. Therefore, it can break. All right, I have just handed you I've just handed you a bag of amino acids. Okay? You don't know any of these amino acids, and that's okay. I want you to pick 12. 12 at random, and what you're going to do is you're going to stretch your protein chain out. This isn't a protein yet because it doesn't have any what? Amino acids, right? Stretch it out, and about 3 inches apart, you're going to start adding these amino acids. This is about 3 inches apart, okay? Some of you are length challenged, okay? That's about 3 inches. So 3 inches from the end and 3 inches in between. Okay? You need 12 on your chain. Doesn't matter which ones. Put 12 on there. Everybody can start adding them on at different spots. Make it happen. Okay, it's a little hard to get them on. You might have to squish the foam a little.
I have 5.
We'll do this half.
Try not to break any of the plastic pieces. I have to order new ones if you break them, and these were free, so I'd rather keep the free ones. Okay, give me 12.
I don't know exactly how long. I don't know. There we go. I know.
Okay, so fill in this gap.
Wow, this is so bad at this. I'm just kidding.
Okay, they should be about evenly spaced. So once you get all 12, try and get them on there.
I'm like already
Alright, get all 12.
Okay, put it right here. Put it right there. Let's go.
Okay, let's do this quick, guys. Do it quick.
I mean, they're close enough.
Yeah, and you can kind of close up on Miss Hall's forehead.
3.
Yeah, I know. Like every time I move, I'm like, that's gonna be in the video. 1, 2, 3, 4, 5, 6, 7.
It's almost a little closer.
Subscribe to me.
All right. Class.
Yes.
All right. Eyes on me, please. Eyes on me. If you're still putting them on, come on. Come on. All right. So I'm going to use this group just to start out. They have their amino acids on a chain. Okay. What is this when we're talking about structure? Primary structure. Okay. All we're looking at is what order they're in. Okay. Eventually, you'll get to know some of these, not by what they look like, but by their names. But for now, in AP, you'll have to kind of know them. But in here, not so much. All right. So I'm gonna hand this back over.
Yeah.
Now it's time to go to secondary structure. Okay. So what do we have to do to our protein? Fold it. Can you just fold it willy-nilly?
No, because this is a
No, I have a little chart, okay? This chart tells me where and how to fold my amino acids. So, yellow bases, see the basement part?
Yeah.
Okay? Yellow bases are all hydrophobic, okay? So, they don't like water. Good, Allie. What's in your body?
Water.
Water. So are they going to want to be towards the outside, exposed area of the protein, or are they going to want to be towards the inside?
Inside.
Okay, so take your protein. And all of your yellow bases need to find an interior spot. Okay, so start folding. All of your yellows need to be on the inside. Look, it made a bow. Okay, I won't do any more of yours. I just did that one. They cannot be exposed to the outside environment. So however you have to fold it to get all of those yellows on the inside, do it.
Thank you, Miss Hall.
All right. Try not to break them off. Are all of your yellows on the inside?
What's the inside?
You're thinking about you're going to make kind of like a blob. And the inside of the blob is going to hide these scared portions. Yes. Here's an example. They had 3 yellows. So I folded all of their yellows to the inside. Okay, so we could even like do this and make horns. Okay, so the yellow needs to be in the interior. All of this can be exposed to water, but the yellows, since they're hydrophobic, are going to be right in the middle. All right, next one. Okay, what's the opposite of being scared of water?
Loving it.
Loving it. What's that word?
Hydrophilic.
Hydrophilic portions. These portions have white bases on them. Make sure all of those are exposed to the outside.
Yeah, all of ours.
Okay, if you folded a white one to the inside because of the yellow, try and twist it or move it so it's exposed to the outside. Okay, so what did they have to do? That's good, good. All right. So they had to bend up their ribbon legs so that the whites were on the outermost edges. This one was here already and this one was here, so they kind of got lucky.
Yeah.
All right. Next, these reds and these blues. Your reds are amino acids that are acidic. Acidic means they're going to have more of a negative charge. Blues are your amino acids that are basic. Okay? They are going to have a more positive charge. What do you think you need to do?
Put them together.
You need to connect every red to a blue.
All right,
If you end up with an odd man out, he can just hang out. Because remember, is water charged?
Yeah, no, that's my try.
Hey,
All right.
is water charged?
No. Oh, yeah, it is. It's positive.
It's polar, right? So it has a positive side and a negative side. So if there is an extra, a positive or negative, it will still like water. It is just only like one side of water. Okay, so do we have all of our whites facing out, yellows towards the middle, reds and blues are connected? All right. Last one. Last one. Some of you may not have this. That's why it's kind of odd. If you have a green, if you have a green, the greens are cysteine. It's a very special amino acid. It is not charged at all. Okay? What do we live in?
The world.
Water.
Water.
Okay? Is water charged?
Yes.
Technically, it's what?
Positive.
Polar. Positive and negative. So if we have an ingredient that is not charged at all, will it like water or dislike water?
Does it not care? Is it just like, it loves it? Is it like the
Well,
hippie in the group who loves everyone?
Is fat charged?
Yeah.
No, fat is not. Does fat like water?
Does it not
The oil and water mixed, Andrew?
No.
No. So if you have zero charge, are you going to be attracted to either end of water? No, you're going to want to hide yourself. Okay? So if you have a green, it needs to go to the center. It needs to go all the way deep in the middle. If you have more than one green, both of them need to be in the center. Figure it out, but you can't negate any of the stuff you've already done.
We did pretty good.
I know, we really did.
How's this going to go?
White ones towards the outside.
Pretty cool.
All right. Let me see one. You had a green. You had two greens. Got it. All right, so check out this protein. Pretty good, right? Andrew, hold yours up.
Oh!
This is long and
That's one.
stretched out. All right, let's look at this one.
Ew.
Another long, stretched out one. Okay. My goldfish, let me see yours.
Oh, yeah, no. We don't
Come on, hold it up.
Hold it
We
up.
don't have it yet.
You can do it. You had a tough one, huh? Look at this. This is a good one. Let me see it. Oh, that's okay.
And they
Just pick it up. Look, they got another one with a tail. They have almost a tail on theirs. Okay, this is very similar to hemoglobin. Okay, this is the only globular one we had. When you see these little bricks like this, these little blobs, what does it make you think? Is it going to be something that turns something on, or is it going to be something that's building? Probably building, okay, or making something. Now, this is really close to what hemoglobin looks like, and we actually get kind of lucky because it's red, like hemoglobin would be.
Wow.
Now, think about it. If we replaced one of these yellows with a white, okay, whites were hydrophilic, how would that change the shape of our protein?
Have a tail.
It would have to bend out.
And it would be
Okay.
hemoglobin anymore.
All right? And it wouldn't have that same shape anymore, would it?
No.
Okay? So if hemoglobin is supposed to be a glob, and we turn it into a long, stretched out protein, will it do the same job, you think?
No.
No. What do you know about sickle cell? How many amino acids had to change? One. Okay? Hemoglobin is supposed to be like this so we can make a nice little red blood cell. What happens to sickled red blood cells? They turn into a big, long, skinny half moon, right? Do you see how that one amino acid matters? Is this going to flow through your blood vessels as well as this?
No.
No, it's going to get caught and stuck and cause clots and all kinds of things. Does this make it a little more real? Trying to figure out how these proteins actually make?
Yeah.
Okay, so that's why it matters. If you change even one, it's going to change the way you fold this thing. Everybody did something at random. Do any of these resemble each other?
No.
No. The closest ones might be this table and that back table, but the twists and turns are not even close. Okay? They have a loop and you have two loops. Okay? So it's a big, big deal to mess up a protein. All right? You have a minute and a half to stretch these back out and put all your pieces back in the bag.
We'll take these. Neither did I. Yeah, I know. Well, me and you will stretch it. Or I don't know what to do with it.
Good job, guys.
Wait, are we supposed to make it straighter?
Oh, sorry. Swirl it back. Swirl it back. I apologize.
Make it really swirly.
And if you are an extra, you can go back.
I'm swirling.
Sorry, I didn't realize it was
Got these videos and I'd be saying so many stupid things. Like, people are going to just be focused. They're going to be like, what? Like, are these two? Like, what are these two?
There's also another two.
And, like, they're probably not going to be able to hear your voice, and they're just going to hear me talking to myself.
They'll probably hear my voice.
Yeah, but it's really quiet.
Yeah, there's an essay to write.
That was like a long, like, yawn. That was like 6 seconds long. What?
All right, frisbee them to me. Not all at once.
Okay.
Yep.
I was like, why is she freaking out?
Hey, present. All right. Left-handed.
Woo!
Good for Frisbee Olympics.
Frisbee Olympics.
All right. All right. So now that we know why proteins are so important and how amino acids really, really have a big deal to do with it, let's keep moving. Let's build a protein. Now, where is this going to happen? We already talked about this. Where are we going to build this protein? At the ribosome. Very good. Because DNA, what?
It never leaves the
Can't leave the nucleus. Why?
because it's not safe.
It's not safe and
It's too big.
it's too big. Okay, so we can't leave the nucleus. So RNA is going to copy our code for us, and RNA is our disposable copy that we can use real quick out of the ribosome and then get rid of. All right. So we're actually built out in the cytoplasm at the ribosome, and DNA is safely tucked away in our nucleus. All right. So RNA, we know what it stands for. How many strands is it? One. Very good. So it's going to be responsible for 3 different things in our protein synthesis pathway. The first thing, carrying the instructions. Okay, it's going to copy. I think we jumped to the other side of the page, correct?
Yeah.
Okay. Okay, so it's going to be responsible for carrying the instructions. It's going to be responsible for getting that message to the ribosome. Okay, and then it's going to be responsible for putting the protein together. Now, there are 3 different types of RNA, and they will not correspond with steps 1, 2, and 3. Some of them will team up on some steps, and some of them will do steps by themselves. Let's look at the individual types of what makes up RNA. What's the biggest difference between RNA and DNA?
It's sugar.
Is it yours?
One strand.
Uracil, right?
Yeah.
It's the uracil. The bases are different, right? We've got uracil instead of thymine. Okay? The reason we do this is because thymine takes more energy to make. Okay? If we leave off one little part of thymine, we get uracil. And it's a lot faster and a lot cheaper energy-wise to make. and it still transmits the signal that we need and the message that we need. So we use uracil instead. Make sense? You're probably not going to waste time or energy. So if we can make this cheaper, we're going to do this one instead of thymine. Yes?
So uracil is a form of energy.
Not energy, no. You have to have, remember, you have to have ATP to put bonds together. Okay, so in order to build the 3 parts of this, it's kind of expensive. Okay? It's expensive to make that one, it's expensive to make that one, but thymine has an extra piece to it. So if we can leave that piece off and not have to worry about bonding it to, we don't have to waste that energy. Okay? All right, we also know that what sugar is an RNA? Ribose, and it's how many strands again? 1. 1, very good. All right, so 3 types of RNA. What's the first type? Messenger, very good. That's this type down here. What's the second type? Transfer. We're going to talk about what it does today. What's the last one? Ribosomal. What's a ribosomal do?
Something with ribosomes.
Makes the ribosome. Okay. All right, so transfer RNA actually looks like a T. It looks kind of like a cross. What does the word transfer mean?
Moving at one place, point A to point
Okay,
B.
moving something from one place to the other. That is all that it does. Okay? The transfer RNA is going to be attached to the amino acid that needs to be there, whatever amino acid the RNA asks for, and it will bring the appropriate amino acid to the party. Okay? So if you're asked to bring a Coke, don't show up with a Sprite, because then we have 2 Sprites and no Coke, right?
Yeah.
All right. And then the last one is ribosomal RNA. It's responsible for building the ribosome. When you get to college and upper level biology classes, they won't even include ribosomes with organelles, because technically organelles are membrane-bound sacs, for lack of a better word, that perform a job inside the cell. There's no membrane here. You can see, this looks a lot like what you all just made. Wound, 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 folded, 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 bent, turned, twisted, protein. That's all it is. Yes?
How does it copy?
We're going to talk about it. That's like the next slide. All right. So messenger RNA's job, really not 2 slides for doing that, but messenger RNA's function goes into the nucleus and makes a copy. Okay, we're going to talk about how that copy actually happens. All right. Most of the characters in that are the ones you already know. You just don't realize it. All right. Then it's going to take that copy to the ribosome, where we're actually going to build the protein. And on this RNA, on this messenger RNA, we have what's called codons. So for every 3 letters that's in messenger RNA, we consider that a codon. So if your there are no D's in DNA. If your DNA reads like this, what is your messenger RNA going to be? U,
A, G, C, G, U.
Okay. So for every 3 letters in mRNA, that is a codon. Okay? Think of a codon like a word of a sentence. Okay? So we're going to put all these words together and get the appropriate amino acid for the word, and then we have a long chain, it's a protein. Okay? So this would be another codon here. Just like a word. Instead of 3, it's a word. All your words are going to be 3 letters long. Okay? Really easy to write.
Wait, on this thing for mRNA, is that what we just did?
Yes, that's the first step. Okay,
That's
on your
all we
baby. That's it.
Oh, that is so
That's it. That's the first step on your baby.
And the dots are like separating codons.
Yes, I already put the dots in there to help you out.
Thank you,
Okay? Because I'm nice.
You're
All right. So let's go ahead and do the first 2. First 2 codons. Fill in your first 2 codons, and everyone's are different. Okay. First 2 codons. Go ahead and do it. You know that if you have an A, you put a U. If you have a T, you put an A. G's and C's are just the same.
Oh, well, I did first.
It's easier if you keep it a little bit organized, but don't go crazy with it.
Yeah, I'm confused.
All right. Is there any questions about what you're doing on the mRNA? We're going to do it a bunch more times. So, all right. So set your baby aside. Okay, set your baby aside. Don't get distracted. I know it's fun, but you'll get your fill. Believe me. There's like 40 codons to code out. All right. Set your baby aside. That's on camera.
I know all this stuff. It's like,
So when your parents ask, why do you have to repeat yourself so much? It's because you all don't do it the first time.
Oh, okay.
All right, and then I have to sing to you.
Yeah.
All right, baby's away. All right, here we go. So,
It's on the floor.
so you just had it. All right, so it looks a lot like DNA replication, huh?
Yeah.
You think there's going to be some sane people in there?
Yeah.
Yeah,
Is
there
helicase
is.
in there?
Okay, helicase is in
He's
there.
my favorite.
All right. All right, so you can see it's only going to make one strand. It's going to open it up and copy one side, and then it'll twist itself back up. So, transfer RNA, its job is to carry the specific amino acid that the codon calls for to the ribosome. Okay? So whatever codon is present in mRNA, tRNA is going to match it and bring the appropriate amino acid. But when I say match, do we ever match A for A, T for T? No. So if this is your mRNA, what do you imagine your tRNA would be? What would it be? A,
T. It would be the original.
We're in RNA, so can we have a T?
No.
It'd be
So it'd
the
be
original.
A, U, C. Do you know what we call the tRNA? What's the opposite of a codon? Oh, good try. Codon. Not quite. What's the prefix that you put at the beginning to say not this? Anticodon. Okay? So on your tRNA, you have what's called the anticodon. It's the opposite of the codon. And you made that connection that it's going to be very similar to what your original DNA strand looked like. All right. Let's put it all together. Okay. Ribosomal RNA, again, makes the ribosome. All right. DNA, how many strands?
Two.
Two. RNA? One. Very good. The sugar?
Ribose and
Deoxyribose and ribose. And what base is present in DNA but not RNA?
thymine.
Thymine. Very good. That little chart should be easy. Flip your chart, or flip your page. What time do we get out of here? 09? 09. Okay, we got plenty of time. You have time to work on your babies. Alright, so flip your sheet over.
What if we're not done copying this?
Okay, well then copy it. I'm not erasing it right this second. Alright, so there is one thing I want to point out to you, and you can add this anywhere on your sheet, front, back, whatever. Just to give you a little bit more of a connection to what we're doing. Alright. So we always start with DNA. We know that every organism has DNA, because anything that's alive is going to have cells, and cells run by DNA. In order to get started with making a protein, what's the first thing we have to make from our DNA? How do we get from DNA to the next step? Can DNA leave the nucleus? No. So what do we make instead? RNA. Okay. So we go from DNA to RNA. Then we use our RNA and its codons to match with anticodons to get what? What's the next step? Amino acids, right?
It's always one step.
Amino acids. And then, once we have a bunch of amino acids, where two or more are gathered together, we get a what?
Protein.
A protein. Okay? Now this seems pretty easy, but this is what scientists call the central dogma. Okay? The central dogma. What that means is this pathway right here in front of you that you're learning today is at the center of every biological process on Earth, and possibly off Earth. Depends on what you believe. Central
Yeah,
dogma.
that's what they decided to name it.
Yes.
I love that name.
Dogma means like philosophy.
Oh.
Has nothing to do with dogs.
All
Alright. So, if you were going to talk about evolution, does this play a part in evolution?
Yes.
Yeah, because evolutionary change is brought on by genetic changes. Okay? If you were going to talk about how to name a new species, we call that taxonomy. Does this matter?
Yes.
Yes, because if it's more like a rabbit or more like a rat, that's going to matter, right? And how would you know if it was more like a rabbit or more like a rat?
Look at their DNA.
Look at their DNA, especially if you uncover a fossil. You can't look at its skin, okay? You can't look at its face. Does it have a cute little nose? Big fat feet?
We don't know yet.
Okay? You don't know that if it's a fossil. You could guess, and we'll do an activity later this year where I give you a fossil and you look at its DNA.
I love that.
And it's related to a chicken and an alligator and something else. I can't remember the last one. And you have to decide. You have to say, I think it would have looked like this. Okay, all I give you is the skeleton. All right, now if we were going to talk about organelles, cell organelles, does this play a part?
Yes.
Who carries this out? Organelles. Okay, so this is at the center of everything. Someone said, well, what about biomes, Ms. Hall? Okay, how do biomes play into this? See if you can find the connection. What do you think, Will?
Because that is just a composition of living organisms with abiotic factors, and all of those living organisms have DNA. They depend on it to exist.
Very good. When you're living in an environment with another organism, you're always interacting. If you're interacting, if Andrew does something crazy, what do I have to do? I either can get crazy too, or I can adapt to his craziness, right? If I adapt for too long, does it become an adaptation anymore? It becomes normal, right? How does it become normal?
You've done it so long.
I've evolved, right? I've developed a new trait, okay? So this happens in real life all the time. Two animals that live in the same environment are always either getting closer together, we call that convergent, converging at a central point, or they're getting farther apart.
Is that what married couples do?
Yes, married couples converge, which is divergent. Good.
That's a movie. Oh, I love that one.
It is a movie coming out. Okay? So in the environment, if you're getting closer together, you would imagine that some of the adaptations that you have, whether it might be coloring, okay? If the forest burns down, mostly, and all of the trees are charred black, are white little bugs going to survive very long?
No.
No. So what's going to happen to all the white bugs? They're going to get eaten.
Oh. Well, I mean, eventually after time,
Well, the white ones get eaten. Who's going to survive?
the black one.
Only the ones that have a lot more pigment, right? So over the course of a few decades, you might lose all of your white bugs and have all of these dark bugs now. What if there's another species in the forest that's attracted to those bugs, when it wasn't attracted before because they were white? Now you have some interbreeding that can occur if the genetics are close enough, right? Because we know that a bear can't mate with an alligator. Okay, not close enough. All right.
I know, right?
Transformer animals. Okay, so this, knowing this process and understanding why this process is important and how this process occurs is huge. If I had to pick one unit that was more important than any others, it would be this one. Okay, this is a big one. All right, sir.
What do you mean, like, to get closer to, like, convergence? Like, when I think
Convergent
of
versus divergent? Okay.
because when I think of that, it's like, I think of, like, two animals, like, suddenly just morph together.
Oh, no.
Just morph together.
Nothing in biology is sudden. That's chemistry. Biology means, or the convergent idea means that, okay, let's talk about like the Galapagos Islands. Okay, and you'll learn soon, that's one of our units coming up. The Galapagos Islands used to be, it is theoried that they used to be connected to Ecuador. Okay, so when everyone was really happy in South America and Ecuador, everybody was good. Okay, kind of like Pangea, yeah. After Pangea broke, we had South America and North America, and then this broke off. Okay?
They could be rearranged into a fire-breathing dragon.
Yes. Okay. So you had these islands that used to be part of Ecuador. Well, as the islands broke off and turned into islands, okay, we separated some species from others. All right, so before, some turtles had some buddies from another species or had some, and now we've got this island that has maybe two of this species and one of the other. Well, if this guy wants to mate, he doesn't have anybody to mate with, does he? So what's he going to do?
Go to the other species.
He's going to go find the other species and just see.
See
It's
if it
gonna
works
work.
or not.
Okay?
Doesn't he die?
He's going to try. If it works, convergence. If it doesn't, what do we have?
Divergence.
Divergence, because all of that species from that island dies off. So there's no person, for lack of a better word, turtle, on that island, under that biome, in that environment that is going through any adaptive changes. All of the species from, or all of the individuals from that species are on another island, going through different environmental challenges and adapting in different ways. And so that would cause those two species to get further and further apart. Not literally, not like the islands keep floating, but in their genetics, because this one might be in a really wet climate. Is it going to pay off to have short nails in a wet climate? Can you dig with short nails? No. Okay, so some of their species, the part of their species that has short nails is going to die out. And only those that have long nails will survive. And so that species will turn into a long-nailed turtle. Whereas this species has really hard ground. So you're going to be able to eat worms and stuff that grows in muck?
No.
You might turn into a vegetarian and eat vegetables and eat leaves. So you don't need nails. So this species will then develop only traits that benefit them in this environment. Okay? Does that make sense, Tim? All right.
Is that why they're different places?
Sometimes, yes. Am I going to survive very long in Africa?
No.
Especially if we still live in huts and things like that. Now, Africa is advanced now. They have cities and roads and
Yeah,
sunscreen.
guys.
Okay. But I had people ask me one time when I said I was from Oklahoma, they said, "Do you live in a teepee?"
What?
And I said, "Well, you're from Puerto Rico. Do you live in a treehouse?" Does that make sense? No. Okay, so everybody is a lot more advanced now. But if I had been born hundreds of years ago, like this, I wouldn't have survived very long. What would I have probably died of? Skin cancer. Okay? All right, and then you can go to that book that we referenced.
Somebody said Congo.
I don't know how that was referenced. All right. Or you can go to that book, depending on what you believe in, and there's a story in that book that talks about how people wanted to build a tower.
Yeah, they got struck by
And
lightning.
no, there was no lightning.
It's not Tower of Terror or
Different
anything.
book. Totally different book. Okay. And then a force outside of them, is what we'll call it, decided to mix up their speech.
Yeah.
Very.
And so the people that understood each other were like, "Hey, let's go over here and live, because I know what you're saying." And those that said, "I can't understand you, you're speaking gibberish," said, "Let's not go live with them because they're speaking crazy," and they live somewhere else. So I mean, it's just kind of what has developed your belief
I
system.
thought in that book, I thought that story, maybe I just, I don't know. that
There was
story-
no lightning.
There was no lightning. No lightning.
No lightning. If I remembered which specific chapter in that book it was in, I would tell you, but I can't remember.
Okay.
Those
It's-
chapters are
it's
confusing.
towards the beginning. All right. And it's called, what's it called? Do you remember the Tower of
Babel.
Babel. What is Babel?
Babel.
What kids do, right? What babies do. All right. So that's where you get the name. Makes so much sense now.
I
Right?
didn't catch that before.
That's it.
Oh yeah, because their speech got messed up.
Yeah.
Oh my god.
It's crazy. Old Testament history, right? All right, let's keep going. We got 9 minutes. All right, here we go. All right, so let's get into the nitty-gritty. We know what happens kind of as a blanket statement, but let's look what happens all like pinpointed, okay? So the 2 steps we're going to have is the first part is transcription. What does it mean to when I say script? Sorry. To write, okay? All right, so the first step has something to do with writing. All right. The second step is to translate. What does translate mean?
Understand and turn it into something other people can understand.
Okay, turning it into something else, and understanding matters,
Yeah.
okay? So going from one to the other, or changing from one thing to something that they would understand, okay? So, does your body, okay, hard thing to say. Does your body use DNA to run all of its functions directly DNA? No. What does it use?
Enzymes.
Enzymes, which are proteins. Okay? Proteins are going to build everything, turn everything on, turn everything off, run every reaction. Okay? So, if your body only understands proteins, but everything in your body is built off of a code in DNA, don't you see that we had to translate something somewhere?
Yeah.
Okay? So that's the second step, getting from DNA to the protein. All right, so here we go. Transcription. Where's this happening? This is in the nucleus. When we're doing the writing, we're in the nucleus. Now, who's doing this? Who's writing the code down? On messenger RNA. So the copy is created in messenger RNA. Now let's look at the steps. Who's going to unzip the helix for us to get in there and make a copy? Helicase makes an appearance, all right? So helicase is back. He's going to unzip it. Is he going to make a replication bubble?
Yes. I mean, so it's not gonna replicate, but it's the bubble.
No. So what would it be called?
A bubble.
Replication fork.
copying bubble?
What are we doing?
Transcription bubble.
It's a transcription bubble, okay? All right, so then who's going to come in and put these nucleotides in place? Polymerase. Is it going to be, hey, is it going to be DNA polymerase? RNA polymerase is going to come in and add the appropriate RNA base to match the DNA bases. Well, not match perfectly, but the complement. All right, and where is it going to take this copy? Where are we going?
Ribosome.
To the ribosome. All right? So the end, we have left the nucleus. The nucleus goes back to being kind of dormant and hanging out. All right, so it makes a lot of sense, right? We're making the copy. Helicase has to open up the helix. We go in with our polymerase, and we put the right nucleotides in order, and then we leave. That's all we got to do. Different than DNA replication, but it uses some of the same players, some of the same ideas. We cannot do anything with the helix tightly wound. Okay, we've got to open it up. And then remember, polymerase, whether it's DNA or RNA, is really good at this stuff. Matching the nucleotide.
After the mRNA was made, does the same thing happen like for things to go back together again? Like this?
Well, all that happens is as helicase is running away. In replication, we skipped a step and we didn't tell you about this, but there's little proteins that are added to the edge of the helix to keep it open. Okay? In here, those don't happen. So once it's unwound enough for RNA to get in there, it will be winding back up on itself as you go. Yeah. Because we don't use those proteins on the outside to hold it open. Those proteins are like a doorstop. They prop it open so that when you're done, it's still open and you have your 2 strands and 2 strands. But this one, we don't need it to stay open. You can close right back up. Good question. All right. So let's do it one more time. Where's transcription happening?
Nucleus.
In the nucleus. Very good. Tell me the main event. Give me it in one word. Not just replication.
Writing.
We're writing
The instruction.
instructions in what molecule?
Well, that's more than
mRNA.
In mRNA. I meant one sentence. Did I say one word?
Yeah, I was like, I don't know.
All right, so copying the order of bases into mRNA. It is that easy. Yes, sir.
Well, when DNA is how does it know which strand to go to copy?
That is a good question. Okay, listen up. Pasta asked the same question that I asked the other day when I was at my little conference that I went to. Remember when I learned about the babies coming out of the mommies and all that stuff? And the gut bacteria and the repopulating.
Yeah.
Remember when I went to that conference? I asked that same question. It has to do with the 3' and the 5'. Okay? How does RNA know which side to copy from? Okay? And as I understand it, it can only make what direction?
5 to 3.
5' to 3'. So when it opens up this bubble, okay, which direction is going to be available?
5 to 3.
Whichever one is going from 3 to 5, because then he can build from 5 to 3. But then if you flip it around, wouldn't it happen on the same thing here, just going the other way? Okay, that's what I didn't make sense of when I was there. Okay, so they told me it has to do with the 3' and the 5' direction, but I haven't quite nailed down how it knows which side. All right? You weren't here for that.
Oh, 5-minute video.
Well, I mean, if you Google
There
it.
are, yes, but I can give all. I can give the conditional hints. It's not my.
I have to write down the ingredients for my food.
All right.
Or else I'll feel
So how does it know?
There are other factors that are involved here. Little transcription
Mallory,
trouble, for lack of a better word.
I know what's in that data. I can write the ingredients down.
And tell you this is about AP bio. All right, guys.